I've selected problem number 54, which is an even-numbered problem. This one involves not just trig functions, but logs of the absolute value of trig functions, which is very exciting. So we're going to have to use our knowledge of trig as well as our rules of logs in working with things. Here's a place where it might be really tempting to try to work with both sides of the equation. Because if I have an equation involving logs, I know if I have that equation, I could exponentiate both sides and get rid of the logs. Can't do that because I'm trying to prove that they're equal, not assume that they're equal. So I'm going to simplify as far as I can, but I am not going to be able to get rid of those logs. When I simplify, I should still have logs of trig functions, probably logs of absolute values of trig functions at that. Okay. So the left-hand side does look more complicated here because that's two terms being subtracted, and here this is just one term. So I'm going to start with the left-hand side. So I'm going to say that's the natural log of the absolute value of cotangent of x minus the natural log of the absolute value of tangent of x. So now I want to think. I'm subtracting logs. Log means exponent. So I'm subtracting exponents. And I subtract exponents when I'm dividing. So I can say this is 1 log for the division problem, absolute value of cotangent of x over the absolute value of tangent of x. So it's the log of this fraction where I'm taking the absolute value of the top over the absolute value of the bottom. Okay. Now, absolute values are kind of nice. They distribute over multiplication and division, not addition and subtraction, but if I took the absolute value of the top, that would make it positive, unless it's 0. If I take the absolute value of the bottom, that makes it positive. If I just take the fraction and I take the absolute value of the fraction, that makes it positive. So I can say this is the natural log of the absolute value of cotangent of x over tangent of x. As long as these parts are connected by multiplication or division, I can just put them inside of one big absolute value sign. That's kind of nice, because now I can just work with these trig functions. So I can say, okay, that's going to equal the natural log of the absolute value. I think to simplify this, I'm going to just write it in terms of sines and cosines. I don't have to. I could try to make it match that, but when in doubt, I always go to sines and cosines. Okay, so cotangent of x, that's cosine of x over sine of x. Tangent of x, that's sine of x over cosine of x. So I've got a fraction divided by a fraction, and the way I would do that is I would say this is the natural log of the absolute value of cosine x over sine x, the fraction on top, times the reciprocal of the one on bottom, so times cosine x over sine x. Okay. So that becomes the natural log of the absolute value of cosine squared x over sine squared x. Now, I could, if I wanted to, stop there and move to the right side. I think I'm going to keep going. I'm actually going to go back now to cotangents because I can see the right-hand side just involves the cotangents, and I'm kind of liking this because cosine squared over sine squared is just cotangent squared. So I can say, still working with that left-hand side, let me just copy where I've gotten to. I've gotten this far. It's the natural log, the absolute value of cosine squared over sine squared. And I'm just going to observe that's the natural log of the absolute value of cosine x over sine x squared, which is the natural log of the absolute value of cotangent of x squared. Not necessary to show that intermediate step. If you're comfortable going from here to here, that's totally fine. Okay. Now if I look at this, I'm taking cotangent of x, then I'm squaring it, then I'm taking the absolute value, and then I'm plugging into log. But if I'm taking in fact, I almost want to write that as cotangent of x squared, just to really make it super clear. Cotangent, then square, then absolute value, then log. Okay. When I'm taking the absolute value of a power, it's going to be the same as taking the power first and then taking the absolute value. So this is the same as the natural log of the absolute value of cotangent of x squared. Okay. These two operations, squaring and taking the absolute value, I can do them in either order. So here I'm squaring and then taking the absolute value. Here I'm taking the absolute value and then squaring. All of this is still the argument of the natural log. Okay. If we think about it, okay, if we just go through some examples, like with a number, if I wanted to take the absolute value of -2 squared, is that the same as the absolute value of -2 squared? Well, this would be the absolute value of 4. This would be 2 squared. 4 is 4. It checks. Okay. Now that's one example. That doesn't prove anything, but sometimes if you're not sure whether you can do something, picking an easy example to see whether it works can be helpful. Now, I don't want to say just because it worked once, it works every single time, but if I think about this, okay, squaring it is going to make it positive, and it's the absolute value times itself. Taking the absolute value is going to make it positive, and then it's the absolute value times itself. Same thing. That's kind of cool. And now I can see how I'm going to get to the right-hand side, because now I can use the power rule for logs. So when I've got the natural log of something to a power, remember that power can come down and become a coefficient. So I can say this becomes 2 natural log of the absolute value of cotangent of x, and that's exactly what the right-hand side was. So kind of neat that we can actually combine our knowledge of logs and our knowledge of trig functions to prove an identity that involves both of them. There are just a couple of these in the homework. Definitely want to take a look at those. Okay.